All right. Um, so where have we been? And we're going to actually take like a step back, go through a few things, but we have been talking about the fact, and we've so far we've really thought of how to analyze stuff in two ways. We've either imagined worlds where we know the where's my we know something about the population's average, right? The population average. And we also know something about the population standard deviation. We started with the question of knowing the population. Say, we know the class as an average scored this on an exam. And I want to know, well, how good was my grade compared to the rest of the class? And the professor tells me the average of the class and the standard deviation of the class. So given just one person, then we can do things to understand where I fall compared to the population, right? We can convert my grade into a z-score and then look to see where that z-score falls. You could even kind of extend that and say, well, is that, so if I'm here, this is the class, and I fall somewhere over here, and I just want to know if I scored differently than the class. That means I'm happy to know if I scored better than the class on average, or if I scored worse than the class on average. So those are the students that I'm worried about. In a more real example, the faculty is always worried about how much service we do, right? Like how much extra stuff besides teaching and research do we do on campus? And we imagine that this is what faculty service looks like. There's people doing an average amount. There are some people doing way too much. And there are some people doing not enough. And so what we want to know is, well, who are these people? Right? We care about them. We need to tell these people, chill out, stop. You need to relax. And we need to tell these people, hey, pick up the slack. Right? And the rest we don't care about. We're like, good job. Keep going. Do what you want to do. So I could find out what is my amount of service I do for the for the school, and I find out it's here. Wherever that is, I can use this number to tell me what does this area represent? If that's where I am, what is this area under the curve? Sorry, I'm trying to get better at this. What is this area under the curve? If this is me, what does that area represent? Yep, good. It is the tail. So what does that tail like signify? We don't know any numbers, right? So it's just like, we see this, there, I know I'm here, and I know that this represents all faculty, right? So this is a curve of all faculty service. What do we know about this part of the faculty then? Yeah. Do more than me. Why are they doing more than me? How did you know that? It's greater than me, right? Exactly. So these are all the faculty that are doing more service than I am, and more because their z-score would be higher, right? And then likewise, then all of these people are doing less service than me. We could draw the line down the middle and talk about from the average to me. But if we were asking how many people do less than me, it's not me to the average, it's me all the way. Right? Good. And so that, we said this is the amount of people, or the proportion, right? The proportion of people who do more service than me. And in this class, we're going to be, for the most part now, almost primarily using the word proportion. And so when I ask you proportion, what is your number going to look like? Where must your number fall between? Between 0 and 1, right? So this is a proportion of people from 0 to 1. We can turn it into percents, but for the most part now, moving forward, we're going to try to resist the urge to talk about percents unless I explicitly say percent. Right? Generally, we want to talk about proportions. So that proportion of people then, I said I want to know if I'm doing more service than everybody else. Like I want to know if I'm really different than everyone else, right? So maybe I'm different because I'm doing too much, but I'm willing to recognize maybe I'm different because I'm not doing enough, right? So here is not enough. And I'm willing to acknowledge that there's some people that maybe I'm doing less than or more than, but I'm willing to accept the fact that I could be doing not enough. And there's some people are doing even less than me. I don't think I'm the least amount of service people. That's your old white professors on campus, men usually. They're doing nothing. But there's someone over here who's doing less than me, but I'm going to accept the fact maybe most people are doing more than me. And so if I say, I just want to make sure I'm not in the extremes of 1% of the faculty. There's 200 of us, about. So I want to make sure I'm not in that bottom or high 1%. So I'm not like the top faculty or the least faculty. If I'm looking for making sure that I'm not in the 1% of faculty who are different, then what is the area to this side? How much proportion is being represented over here? 0.01 for the whole thing, or just this?
Oh, I was just trying.
Oh, yeah. So this percent, right? Great, because we're talking about proportions now. So let's turn that into a proportion. And since we've now turned into a proportion, and I'm talking about what I want to compare it to, that is what we are going to call alpha, right? That is how much under this curve are we willing to be less extreme than, right? So it's that point where if I observe a value here of myself that is more equal or more extreme than 0.01 proportion of everyone, then I'm going to be like, whoa, I have to fix what I'm doing. Yeah. And since it's now in alpha, and I'm saying like, I'm willing to accept a state in the world where I don't do enough, and I'm willing to accept a state of the world where I do too much, how much proportion is on the right side? How much is this 0 to 1 over here? And how much is over here on the left side? .005, right? So we're going to divide that by 2. For me to say I'm different, I need to be at least equal, if not more extreme, than 0.005 of the people on this side, and different or equal or more extreme than 0.005 on that side. If I fall anywhere in here, I'm going to tell myself it's time to reassess my service. And so even with just one person, if I know what this shape is, and I know something that it's like the mean or it's a normal distribution, and I know the standard deviation of this, like I can test against me. I can get a p-value. If I ended up right here on this line, then the p-value, which represents the proportion of people or proportion of observations that are equal or more extreme on the curve, would be this area and that area. And so if alpha on a two-tailed test means we divide by 2, we have to split that alpha into both tails. When I look at the proportion that are better than me over here and say, all right, there's 0.005% of faculty who are doing more service than me. But that's not my question. My question was not who's better than me, but who's different than me. If it was true, I was doing an equal amount. And so to get the p-value for a two-tailed test, if we're dividing by alpha by 2, to get a p-value, we have to multiply this by 2. So for a two-tail p-value, especially when we're thinking about how our tables only give us one tail. Right? Like everything is the area under the curve to one side. Two-tail p-value, we need to multiply area to tail by 2. Did I lose anyone? And remember our agreement, if we engage in class today, then we get equations moving forward. And I'm not saying you have to be like, okay, sure, yeah. But I just want, like, I want to make sure that we're on board with this stuff because this is where now we're going to be kind of moving forward from here, yeah. So, I mean, I made it so my Z score was also the score for the Z critical. What is that number? 2.58. Yeah. So let me clear this off. Clear this off. So we did our math. We've done math. Dr. C had some Dr. C's hours. Dr. C's service. And we had subtracted it from average faculty service. And we were told in the problem that the standard deviation for all faculty, because Dr. C is now in charge of collecting that data, is some value. So you know the standard deviation. What you're not told is how many other people are there. You're not really given any n. The problem has no n. The only problem is that there's, the population average, the population standard deviation, Dr. C exists. All the information you're given. So when you're writing out, what do I know? You write out, okay, well, we know X is Dr. C number. We know the average of the population is faculty, and we know the standard deviation of said faculty. But then you get to n, and you're like, great. Then we're doing something different. So this is, we're kind of doing, I think it was problem 6, not, might have been 8. I think it was 6. And so since we don't know n, we're not doing like not thinking about that dividing by n piece. That doesn't exist right now. We're talking about one person how are they different? And so we find out that Dr. C's Z-score ends up being a positive 2.58. And I said we wanted an alpha of 0.01, and I want two tails. That means I use the word different, right? That I want to know if I'm different than that. In my head. I don't know what the numbers would be to get there. I just know that. You did the math. Congratulations, the math is 2.58. Sorry, don't have the example will work with 2.58. So if my z-score, maybe the question just said, Dr. C's z-score in terms of service is 2.5. I'm gonna skip it to you. You know, an alpha 0.01, you know, two-tailed test. We're still missing like one piece to know if I'm different. What is that piece we need to know? Comparison value, right? Like what is that? We've used the phrase the cutoff. We've used the critical. Like, what am I comparing to? When I say, am I different? Different compared to what? What is my difference? Where am I going to say I'm different? And I said, well, it's going to be that proportion of 0.01. So in our heads, we know that a two-tailed test of a proportion of 0.01 means that we're looking for half of it to be over here and the other half to be over here. That should be written like that. This area is 0.005 and this area is 0.00. So we multiply this by 2, we get 0.1. So that means 0.005 in each tail. If you went to your Z tables and looked for what is the area, or what is the Z-score to have 0.5% your table are in percent under the curve, to the right of the curve, right, or to the left, but it tells you in one tail. If you go to your Z table and you look for the area under the curve for 0.5, or here, where the number that represents 0.5 in one tail is up here. You have 0.51 and 0.49. That is the percent that is in one side of the tail. And since we don't have a real number, we're going to say that's this guy. And so we need to compare to a Z cutoff of 2.58. So I got there because I just know that for 0.005 proportion, it's 2.5. So now, give me a blank slide. we know our cutoff score is plus or minus 2.58. Because that's going to represent the minuses over here. I'm willing to accept that I could be really low in mine. Negative 2.58. And I'm willing to accept that I could be really high, positive 2.58. And I find out that my z-score is 2.58. And so, if I ask, okay then, now that we know this, what portion of faculty are equal or more extreme in their service compared to me? So that was my question, right? How equal or more extreme am I? What proportion of faculty are equal to me or more extreme? Assuming that the null is true, which just means like, assume that we all do the same amount, sir. We're all equal. Not true. Yep. And what else? So, are like more extreme than me, right? Like the question is who is more extreme? And so there are these people, they're more extreme because they're better. They're doing more service than me, not better, probably worse. Right? We need to chill out. And there are these people who are also more extreme than me. And they're doing such an extremely low amount of service that it makes them like different than what we would expect. We would expect everyone does the same amount. How service is supposed to work. We all do it together. But that's not true. In reality, some people are really extreme in how much they do on both sides. So the proportion of people who are equal or more extreme than me is what? Point oh one, right? Or if we want to translate that in our head, 1% of the faculty are equal or more extreme than me. Because, and that phrasing, I keep repeating, equal or more extreme than me, what proportion of observations are equal or more extreme is the definition of a p-value for a two-tailed test. Right? The p-value represents who's left. What people are more different than you. And an alpha value is saying, I'm willing to accept this amount of people to be different than me before I start saying something is wrong. I should only start thinking about my service if 1%, if I'm in the top or bottom, area, that I'm in the top 1% most extreme faculty members on the service. And so that p-value is equal 0.01. And our alpha, we said, was 0.01. And my question was, what proportion of people are equal or more extreme, right? Like that's what I'm trying to investigate. And I'm willing to reject the null hypothesis that I do in average amount of service. Like I'm going to be willing to say, no, I do a different amount of service if turns out that my service is equal or more extreme than 1% of faculty. Do I reject the null hypothesis and say it turns out I am equal or more extreme than 1% of the faculty? Or do I fail to reject the null hypothesis and say, actually, I am not significantly different from the average faculty member? equal or more extreme? Yes, I would. Why would I reject it? What word in equal or more extreme is helping you say reject? Yeah. It's equal to the alpha level, right? Yeah. 0.01, they're equal. And I said I would be willing to reject it if I was equal or more extreme. To be more extreme means that instead of here, maybe I'm out here, right? My z-score is increasing. We said that as this goes to the right, my z-score gets bigger. If my z-score is getting bigger, then the area is getting smaller. Right now I'm pushing out my observation over here. Only this proportion of people are doing more extreme than me. So that means the area for P would be getting smaller. You get this in our sum number. And so the alpha tells us how small does this P need to be. P also ranges from 0 to 1. And generally, we're looking for three things. You'll pretty much only ever see me ask a alpha value of 0.05, or I need to be 5% more equal or more extreme than people. We have an alpha of 0.01, 1%. We see an alpha of 0.001, so 0.1%. And sometimes we see that alpha of 10%. Following that. So given just one person, we can find out where they stand compared to everyone else. We just get their z-score, we compare it to the z-score of whatever we're looking at, like the z-critical value, that comparison value, and we decide is it more or less or equal to it. Yeah. That's the cutoff z-score. Yep. So that was one of those problems in the problem set where it was just, here is the average. A student takes a test and they score what? And then you get asked some questions about that student. And while the first thought is like, well, I can tell you proportion of people, better or worse, or between two ranges, you also can extend that to then tell me about the proportion of people more extreme, or the p-value, compare it to the alpha. All of that works out. The next thing we did is that, okay, but what if we were doing more than just one person? Right now, what if we start collecting some data? Where I know what my, again, class average should be, population of students. I know what that population average is. I know what that population standard deviation is. And I know my sample, right? I'm sampling a bunch of students. And I know my sample average is, okay, and I know how many people I sampled. Number of people sampled. Now we're given a number. Now we're not just talking just about one person. We're thinking about a sample of people. So that's what we were doing last week, thinking, what if it's not just one person we're observing, but a sample of people we're observing? But we still know the population's mean and the population's standard deviation. So from this, we start applying the central limit theorem. That we know what that sample average is, that's going to be X. We know we're trying to compare it against the population average, mu. And since it's a sample, rule 2 of the central limit theorem says to get an understanding of the standard deviation of the sample distribution of sample means. Comparison distribution is what? How do we calculate this new standard deviation that we're coming up with? Over the square root of n. So we have that standard deviation of the population, sometimes written like a little O hat, divided by square root of n, square root of our sample. We use this formula when we are given the population's average, we're given the population standard deviation, we're told it's a sample, and then we also know how many people are in the sample. In this kind of question, you're told the n. So since you're told what that n is, and you're told this piece in particular, this is going to kind of distinguish it from pretty much everything else moving forward. Then we're using this formula. And then everything repeats. We're looking for that cutoff score. We're looking to figure out what our z-score is compared to that cutoff score. And we can translate those into a p-value. What proportion under the curve is more or less or different, depending on what we're interested to find out. Yes.
Is that a function that is equal?
Yes, sorry, thank you. Then everything else stays the same. Really, this is different because now we have n, we have that information, so we're going to add it into our equation. Why are we doing this? It's because the central limit theorem, we've now taken a sample from the population, and we're trying to ask, like, is this sample part of the population, or is it different? That's the question. We're trying to find out differences. And this gets to the last point of things we need to review, which is, what are we asking, right? And so in statistics, we start from a state of the world that sounds silly sometimes. But we start with the assumption that everyone is equal in everything. Right? The reason why I am doing statistics is because I want to show that people are different. We start with the assumption that everyone's the same. In this case, we draw a sample out, and we're saying, I'm going to assume you're from this population, and that's why we're going to compare it to this population that we know about. We know about a population of people. So on the test, we knew something about non-drummers. And we knew something about the non-drummers standard deviation as well. And then we learn about drummers. We are assuming that they are the same until proven otherwise. Not even really proven otherwise, until suggested otherwise. That's the research question. In all of how we think about statistics in psych, it is, I am assuming these two groups are equal until statistics tell me I should treat them different. So sometimes you can say, I want to know if they're less in their attention span. Sometimes say more, sometimes say different. But we're always starting from an assumption that they're equal. So then what, in a question like this, where we're trying to understand drummers versus non-drummers attention spans, is the null hypothesis. Same attention span, great. Right? If I was asking different, right? Like, yeah, great. And so the null hypothesis, sometimes written HO, sometimes said just null, is the state of the world that we are starting with. We're always starting with the assumption that they're equal. So that is drummers equals non-drummers. That is the state of the world as we currently know it. We might call them something different. One called drummers, one called non-drummers, does not matter. I do not know if they have different attention spans right now, so I'm going to assume that this is true. They are the same. So we say, like, assuming the null is true, means that assuming that this is true, how extreme of an attention span must you observe to change your mind? And that's the alpha value. What proportion under this curve must they land in for you to say, wow, maybe they're different. Maybe they're not the same. And so then the alternative for HA is depends on our research question. Here, just by writing this, I know that I'm talking about a two-tailed test. And so because of this two-tailed test would say that drummers are not equal to non-drummers. I am not stating which direction they're different. They could be more, they could be less. I don't know. I just want to know if they're different. So they're not equal to each other. Let's say I had a guess, right? So in the question, it has a guess. It says, I want to know if drummers have lower attention spans than non-drummers. If that's the case, what is my alternative hypothesis? So it's drummers have lower attention span than non-drummers is what I want to find out. Is this true? Then what is my alternative? One second. Not equal to, but less than. Less than. Yeah. In a one-tailed test, the alternative is a single direction. Though drummers sorry, just making sure, are less than non-drummers. And so what does that mean for the null? What are we assuming about the world to be the case? In this situation? Good, so that's half of it, right? So one state of the world is that I would be wrong on my guess if drummers have the same attention span as non-drummers.
drummers have a higher attention span than non-drummers.
Yeah, good. So I am wrong. My guess about the state of the world would be incorrect if they were equal to each other. That would be wrong. That's not less than. Or if it turns out that drummers had a greater attention span, that also would be wrong. The alternative is like what we're testing to see. On a one-tailed test, we're being specific. We're giving ourselves like a direction. But that means then we're wrong if they're equal to each other. And we're wrong if it's the other direction. That's also wrong. On a two-tailed test, I don't want to guess the direction. I just want to know if we're different.
With a two-tailed test, are the only alternative always going to involve the equal sign and the not equal sign?
Yes.
And then the one tail always involves the greater, less than.
Indeed. I saw one person and I was like, I've never seen that. I think that kind of is, that works. I think is that for a two-tailed test, someone wrote like a less than or greater than short. That covers both possibilities, but you could also just write not equal to. But yeah, if you want to write out both tails, basically, that'd be acceptable. But in my mind, yes, it's easier just to assume they say two-tailed, I need to write something that has a not equal to, and something that says equal to. If it says one tail, one of them has to be a mouth, and the other one has to be a mouth with a chin. Well, this one. This is from a paper that we have under review right now. I'm shocked. It is what I call my zombie paper because we've been working on it since 2018. It won't die. But it just got like revise and resubmit, which means they're giving us a chance to publish it in a really big journal. And I'm shocked that someone actually thinks it's good because it's terrible. But in it, we write our hypotheses really explicitly. So you can see here, there's like bold to it. And so honest disclosures are this idea that I can go to a store, an Apple store, and you're like, hey, I want a phone. And you tell them about the phone, and they're like, bro, you don't want an iPhone. You should go get an Android. Like, oh. Thanks. Right, when someone is honest and tells you, we're not selling what you want, go somewhere else, right? Or like, vote for the other guy. They're better than me. No. Those are honest disclosures. And so we say, buyers who receive honest disclosures will express greater intention to purchase the seller's other products or services immediately. What is our alternative hypothesis? I think when we're reading research, it's easier to actually start with the alternative to then figure out the null. And is that our null or alternative? That would be our null. Less likely, right? So it's the state of the world we're assuming where it's kind of, so buyers, you said buyers less likely, but less or equal to purchase when faced with honest disclosures versus not faced with honest disclosures. Or just like generally in the world when they're experiencing this thing, we think that they're gonna have no effect, right? Like telling someone go buy something elsewhere is gonna be like, whatever, I want an iPhone, give me an iPhone. Or somehow saying, you know, give me an or you don't want an iPhone, like, cool, see ya, and I leave. And I don't give you any more money. Makes sense. You know, that's, someone tells you you don't want something, you should leave and not buy anything. Honest disclosure, sorry, I was trying to signal what we were talking about. Anyone ready now? So if that's like the state of the world, right? And sometimes it sounds like a silly state of the world. Like, of course that's gonna be the case. Like, if someone tells you not to buy something, you're literally gonna buy something. Turns out. And so what we're trying to prove is that's not true. That's why we're doing this research. We think that actually, when someone tells you you should not buy from me, you're like, cool, can I have a chocolate bar? Yes. That we want to reward that person for being honest, and I'll say thank you. And so in this case, we're saying buyers, and we see the direction here, right? Express greater. It's telling you a direction. Greater. Buyers who experience this are going to want to purchase more things compared to not. And what you don't have to worry about is the statistics, but in research methods, you find out this is a lie. We actually do a two-tailed test. Yeah. So our hypotheses are generally the alternative hypothesis. Yeah, so the null hypothesis is kind of like a null being like zero or like without, maybe. And so without a hypothesis, what is the true state of the world? Alternatively, what could be the case if we do some research? Here's a hypothesis. So the null kind of telling us like, without a hypothesis, we assume that this would have a bad impact on things. But alternatively, I have a hypothesis that it actually would have a good effect. Maybe that's not something.
This might not make sense the way I'm thinking of it, but when should you assume that the null means that there's no difference, and then when should you assume that it's like dots?
So if you're at if the null, if you want to write the words like, you know, the null means that things are not different from each other, that's going to mean that you are understanding this test to be a two-tailed test. So two-tailed test, the null should two-tail. It's going to be not equal. One-tail test, it's either going to be this or that. That answer the question?
Yeah.
And why? It's because it's kind of telling us something about the direction that I'm assuming the state of the world is a certain way. But yes, as I said, in stats, this is how we should read the sentence. But when you actually start reading psych papers, we just lie. We tell you a direction, but then we test it like there was not a direction. But I'm not going to ask you to interpret it. I'm going to ask you, like, literally, what is it asking? And this literally is saying it's a one-tailed test. Because I am guessing a direction. So far, those are the two tests we've covered. These tests when you only have one person, and a Z test when you have more than you have a sample of people. Today, recording and this week has been talking about the t distribution. Sorry, skip too much. Come on. Where am I? I don't know. I guess I lost it. Oh, geez. I didn't want to do that. So let's look at me. We'll start here. Here's a question. This time, the question is going to give us new information. Different tests, new information. We learned that we have 61 students taking a test or answering some questions. So we have an N of 61. They rated their stress levels at 4.84. So their average stress is a 4.84. So this is of my sample. The average of my sample. I also know something about the sample's standard deviation this time. The standard deviation of the sample is 1.58. Then you're asked, okay, is this group of people different from 4? So we can translate that to, we are comparing our sample to a population distribution that has an average of 4. This question is, we can kind of translate that to saying the population mean that we care about, that comparison mean, is 4. What don't we have in this question that we've had in prior questions? What piece of information is missing? Good point. I didn't write down the alpha. Alpha is given to us of 0.1. Thank you, Doc. Alpha is 0.010. Yeah. Population standard deviation, right? I don't know. I know the populations mean what I want to compare against. I want to compare against a population that has a mean of 4. But I don't know what that standard deviation is of population. And this is statistics now. Now we've jumped into it because the truth is we never really know the population's standard deviation. We actually don't know the population's average. We take guesses. Is it greater than or equal to 4? I don't know what every student's stress level is here on campus, or every student's stress level is in the United States. I definitely, if I don't know that, I definitely can't tell you the standard deviation of that population. So we don't have population standard deviation. Once you lose population standard deviation, we are no longer doing a Z test. Let's go, it's dead to us. Instead, we have a test that is just like it, but it's called the t-test. So the t-test looks very similar to what we've done, except with some minor modifications. And so again, everything still applies. What we're doing, we're imagining that we've sampled some people, we have 61 of them, from some population. Right? Grabbed in those people. We don't know what that population standard deviation is. We know what that distribution of people, imagine we're drawing out those 61 from this population. We want to know, like, okay, are they different than if this population had an average of 4? Not only different, we're saying greater than. In fact, we said greater than means what kind of test? or tail test, tailed. One tailed, right? So I'm telling you a direction. I want to know if they're more stressed than 4. So then, what is our alternative hypotheses? What are we testing to find out? Greater than 4, right? So stress of students is greater than 4. That's our alternative hypothesis. What if we didn't have a hypothesis? What is like the state of the world that we are kind of assuming to be true, still shown otherwise? Well, what would make me wrong? Less than or equal to 4, right? So that right now, like the state of the world is that Stonehill's not going to care too much about your stress levels because they're assuming that your stress is less than or equal to the assumed population. Why do we have to care if you're average? You're not gonna put us fun. The comparison distribution changes a little bit for the t distribution, and that's why we need a new table. Instead of the z table, there's the t table. The thing that makes the t distribution different is that it has to account for the fact it's representing the population. It needs to make up that standard deviation of the population that we don't know about. And so we do that through a few ways. First, now we start using this piece, n-1. n-1 is called degrees of freedom, df. And wherever we have in our equations thus far, where we've done n, now we're going to start thinking in terms of n-1 degrees of freedom. And so we know that there were 61 students, right? That's what the answer said. 61. So then our degrees of freedom is n-1. So what's the degrees of freedom for my sample of 61 students? 60. So df is also a piece of information we're given. The df is 60. And the thing about the t distribution is that degrees of freedom really matter. Because the degrees of freedom for, say, 2 degrees of freedom, I have 3 people, and I'm trying to estimate them for everybody. It kind of looks like, so the tails are just much thicker. And as our degrees of freedom increases, this curve becomes more tightly together. Remember, this is actually what was happening with the central limit theorem. Right? As we increase that sample size, the curve went from flat to getting up, and more tight, right? To getting tighter controlled. That is what the t distribution is doing. As we increase the number of people in our sample, the t distribution becomes more and more normal looking. Central limit theorem, everything copies over. We're going to assume that that comparison distribution is 4. That comparison value is 4. And the variability is still n minus 1. And why are we calculating degrees of freedom? Because degrees of freedom doesn't come into the math part, it comes into the table part for right now. So how will we do this? Well, we know that we're looking for 10% in the tail. We have a degrees of freedom of 60. And we've used the equations that we already know. Calculating standard deviation is the standard deviation divided by the sample size. You know, all that information, all we need to know is what is the cutoff score? What represents 10% in the tail in one tail, because it's a one-tailed test for degrees of freedom 60. And so then you go to our t-table, which looks slightly different. It now looks like this. We're at the top. You see here, we have percent. This table is giving you two pieces of information. Equal 61. Equal 4.84 of the sample. Standard deviation of sample 1.58. The top comparison value is 4 and an alpha of 0.10. So we have two columns now, or two like sets. It's showing us one-tail test, so percent of the curve on one tail, or two-tailed test, percent in the curve on two tails. We have 10% in one tail, or 5% in one tail, 0.01% in one tail, 10% across two tails, 5% across two tails, 0.1% across two tails. But now we don't have that like z value on the side. We have degrees of freedom. And that's because the distribution shape changes depending on the degrees of freedom. And so which column are we looking at? 1, 2, 3, 4, 5, or 6? Point 1.10, right? On the one side, on the one tail test side. So we take that table and we look for where does 60 line up? Try to draw one. This one, this one, this one. This was 0.10, 0.05, 0.01, 0.10, 0.05, 0.01 for 60 degrees of freedom. What is our cutoff score for degrees of freedom of 60 with an alpha of 0.1, a one-tail? Yeah.
1.296.
1.296. So we're on the left side because it's one tail. We know our degrees of freedom is 60, and we're looking for that 10% in one tail. So 1.296. What do you notice about this column here and this column here. They're equal. Why are they equal? We have two check tests, right? So let's just kind of go over what's happening here. This is saying over here, one tail, 5%, right, or proportion of 0.05 is over here. That's what that number represents, and for a degrees of freedom of 60, df is 60, that was 1.296. Negative. Why is it negative? Why did I add that negative? Right, I'm on the left side. Right? The left side is negative side, right side, strong side, positive side. If I then said, okay, but what if I wanted a two-tailed test of 0.1, what percent of the tail is on the left side of that number? So I'm going to be 10%. How much goes on the left-hand side? Right, 5%, right? At 0.05, which is, we just did it, right? And so over here would be positive 1.296, and there's 5% on this side. And so for a one-tailed test, 0.05 on one side is the same number as doubling it for a two-tailed test. So now that we've used our degrees of freedom to find our cutoff score, let's plug in everything else that we have. And we got these numbers from certain places. We have the sample mean provided to us. We had the expected value if the null is true over here. That's the comparison value. And we had the estimated standard error. We've learned how to calculate that in our z-scores. So that was the population. We don't know the population. Well, what do? We take the standard deviation of the sample. We're going to sub that in. By 60. And equals 0.202. Now here is my last tip to help you and us. Part of our learning objectives is to get good at understanding how to report statistics in APA style. In APA, once we get to a number, we round it to 2 decimal places. And it's just good practice to write it. So here I'm not using 0.2, I'm writing 0.20. We round to 3 decimal places, I should say, for p-values and alpha, wherever. We don't really calculate alpha. But for p-values, it's 3 decimal places. When you're talking about proportion under a curve that is equal or more extreme, 3 decimal places. You round off to a third. Then the last thing is that you've noticed our alphas are written like so. Right? where we don't put a zero in front of this thing. We don't put a zero in front of it because it can't be greater than one. Like, that's not possible. It's a proportion. It goes from 0 to 1. And so we never put a 0 here. And because P is also a proportion, you never leave a 0 for P. So P is always strictly 0.00 something. Never 0.00. I'll just draw a red line through it on your practice problems. Nope. Just drops a 0. Okay. We have our comprehension check number 2 on Friday. You asked questions, I guess, so I'll provide equations. Now, I think I've been so overloaded. I'm pretty sure someone has asked, can they see their stuff, but I haven't responded to it. Please just bother me again, or come see me now, whatever it is. Like, I wanted to show you that, or if you're like, just tell me what I got wrong and where I can get it. I can also email that to you and do that for you. Yeah. I will be providing it to you, but you won't need the key for this one, but
Oh, there's one that's on this.
I don't think so. Does it say on the plate? I don't think it says that on the plate, yeah. You will have, I will give you the details, so there we, these are not finished.
Memorize.
I will give you the equations. More equations than you need, but I'll give you the equation. Fine. I'm guessing you like clicked like 3, but it was like,
Yeah, I think
one
I
that was
think
like the wrong one.
That was so fun. But, I was wondering if I could send you like, because I was on one page, do the problem set. I could like, email to you.
Yeah, you
or
could-
the.
I mean, like, it doesn't really like, it's, you know, it's effort and,
Yeah.
like, you know, but yeah, you can send it to me and I can, I'll make a note on your assignment about it.
Thank you.
It did make me laugh though.
Yeah, no, maybe.
I appreciate it.
I was so confused, I was like, because I saw the comment like bird. Like, oh, that bird. Good there.
You too.
I was just curious about, I did 4 of them in the last one, and I got 2
Okay.
of them